we will be doing this. Okay, just a gentle reminder. Homework 1 will be due on Friday, and 10 days after the due date of homework 1, we will have homework 2. Okay. So let me talk about the probability. So let's very briefly review what we have done. I guess last time we just covered the axioms, so we will cover some probability rules today, and then we'll talk about Bayes' theorem, right? I think last time we more or less stopped at then last time we just stopped somewhere here. Am I right? Am I right? Somewhere here, right? Is it last time someone stopped somewhere here? Yeah. Okay. So let us briefly review what we have talked about probably so far. So if you still recall, I mean, probability that we have been working on in the high school is the classical definition of a ratio. Okay, is you can repeat the random experiment many times and look at the ratio of how many outcomes are favorable to total number random experiment you are doing. Okay, and that is coming from empirical idea, or what we call the frequency list approach. And this is good for a lot of purpose, but it's not general enough. So that's why the modern probability model actually defined based on what we call an axioms. So we will be defining probability based on 3 axioms, okay, and that is consistent with the idea of long frequency. Of course, it's more than that, but it is consistent with that. So just remind you, what are the 3 axioms again? The first axiom said probability are just a number that's between 0 to 1. Okay, and do note that this definition of probability just have no empirical content, but basically just give me the sample space, give me whatever events, I put a number to it. Okay, the number I put in is between 0 to 1, consistent with the idea is a fraction. And second axiom is saying that the sample space would have probability 1, so which means that we have a complete knowledge about what's going on, and there's no surprise in terms of outcomes you observe from the random event. And the last one is the most important assumption of all, which said the following: probability event, okay, if the event consists of a union of mutually exclusive events, that is what it means. It's just like all the event together, all the outcome together, then it's just sum of the probability of each outcome. In the other word, it means that probability satisfy what we call additivity idea. It's just like if the event can be cut into multiple parts, the probability event will be sum of the probability of each parts, as long as each part are not overlapping. Okay, that's mutually exclusive, right? In that case, that is what this assumption is. Okay, I hope this is clear. Just a gentle reminder of some operation of set, because we'll be talking about this very soon, because we today talk about some probability rule that will rely on the operation of sets, intersection, union, and complement. Okay, just to remind you what is intersection. Intersection means you just find all the common outcomes in both events. Okay, in the case of rolling a die 1 up to 6, say E is even number and odd is always odd number, then the intersect, okay, will be empty because they don't have common element. But intersect of E and large there will be common element 4 and 6. Okay, so if you intersect odd with large, we'll just only 5. So I hope that is clear. And we also have union. Union is include everything, so it's just like everything is there. And so if you union E and O will be just everything. Okay, just the sample space. Okay, just to remind you, the intercept will be just overlapping area. The intercept is just everything. It's covered by either of them. Okay, and finally, complement is something not there, is in the sample space, not there. Okay, basically just look at the sample space, you kick out the things you belong to it, is the complement. So basically this event E complement with everything outside this E. Okay, so here we also have what we call mutually exclusive. That means that the intercept is empty. Okay, they can't happen at the same time. If one is true, the other is wrong. Okay, but it does allow the possibility that none of them is true. Okay, it just rule out that they happen at the same time. And the other is mutually exclusive. Is another in another case is where one of them must be true. Okay, which means that or both of them are true or fine. Okay, this just rule out all of them are false. Okay, say must be one of them is true. Okay, so just like the completely opposite case, right? One is cannot be all of them is true, both of them true. One is one of them must be true. Okay, so when we have partition, that is they are mutually exclusive, exhaustive. That is the standard idea that they are more or less you can cut them into different pieces, right? This is related to the axiom 3 we have, right? The axiom 3 said if you do the partition, then you just divide the event into multiple parts, then the probability of the whole is just probability of sum of the parts, right? So that is what axiom 3 is. And as I mentioned, as technical cases, the real power of axiom 3 lies on the fact that it also holds for infinite partition, but that would not be our concern because for our class, but that would be something you would know when you go into deeper into probability theory. But just let you know why we need this, and this is an important idea, right? Because the classical working of the probability, say the ratio, the very beginning, we have this one, right? This one would work if everything is finite. This actually works, right? Axiom 1, 2, and 3 is very natural under this idea, but axiom 3 is not, when it extends to infinite partition, is not very clear. So that's why it takes mathematicians 300 years to come up with axiom 3, more or less along that line. So if there's no problem so far, then we'll proceed to talk about probability rule. Basically, everything we learn from the high school, there are many rules you learn from high school. We're trying to show that everything can be derived from the 3 axioms. Is that okay? Is there any question? If no, then we go to 3 axioms. The rules that derive can be derived from these 3 axioms. The first rule probably you know also from the high school way. Easy one is if we denote A, C by the complement of A, right? That's not the thing is not in A, and the probability A will be 1 minus the probability of the complement, or the other way around, the probability of the complement is 1 minus probability of A, right? Because it's just small. Or in the other word, is say probability of A plus the probability of complement is equal to 1. So what I'm saying is probably is not entirely clear, but I think that is very straightforward from the math, right? This is the same thing, right? Or you can write the following: probability of A plus the probability of A complement is 1. So basically, 3 of them are the same expression, and the last expression, right? This one, okay, this one, right? Which is directly followed from axiom 3 and axiom 2, right? Actually, we saw in the next slide, right? Why this is true? Because A and A complement is a partition, which is mutually exhaustive and it's exclusive and exhaustive, right? The sum of them is the sample space, right? So that's why this is equal to 1. This comes from axiom 2, right? And the sample space is union of these two, right? And intersects empty. So the sum of them is equal to the sample space. So that's why this is 1. Okay. Is that clear? Why this is true? Okay. So if the proof is like this, right? Very simple proof, just go over it because let's give you an idea why we need axiomatic definition rather than we define or just go through this only proof, I guess. I mean, maybe one or more two proof, but this is the simplest proof is like axiom 3 said this sample space, right, is a union of the two, and because they're mutually exclusive, exhaustive, right? So that's why we can write equal to sum of these two, this from axiom 3. And axiom, actually not 2, axiom 2, not 1, axiom 2. Axiom 2, sorry, there's typo here. Axiom 2 said probability sample space is actually 1. Okay. And that's why you put 1 here, right? So that's we end up with this one. And just rearrange whenever you like, then you have what we want. Okay, so that is very trivial proof there, but it really relies on the axioms, and that's why you see what we will learn for the rest of the rules today. We base on all the axioms here. Okay, is that clear? Is there any question? If no, as I said, the proof is not important in the sense that when you apply, but it's good to know why it is true, right? Just not say, okay, you believe this, and then we try to convince you that everything we learn is coming from the 3 axioms that we emphasize. Okay. Just to illustrate an example why complement rule is a good one is because of the calculation of the event itself can be complicated, and very often you want to calculate complement. For example, is the following question where we are asking, what is the probability that you roll a fair die? What is the happen when the face value less than 6? Okay, and less than 6 actually have 5 outcomes, right? But if you look at this complement, which is more than or equal to 6, only you have only 1 outcome. Okay, 1 outcome is much easier than 5 outcomes. So that's why you calculate the probability of that 1 outcome, and you 1 minus that use the complement rule, then you get the answer. Okay, so that's why we use this. Of course, this example is trivial. You say calculating it directly is fine, but that's more clear, more clean. So here, look at this question is less than 6, right? The complement is no less than 6, then which is only 1 outcome, right? It's only 6 because there's 1 over 6, and use complement rule, you get 5/6, right? So that is make your life easier. Okay, so this is rather simple. I hope there's no question on that. But let's see another. The graphically is like this, right? You don't know, the inside can be very complicated, but the outside you can count easily. So that's why you count it this way. So that is a kind of shortcut. If you cannot go in a strict way, you can go in the other way around. It's the standard way you do math, right? This rule actually applies more than A and the A complement, but rather if you're the sample space, right? You can partition the whole thing, right? So just remember the idea here is like we have a sample space S, right? And we may want to cut it into say A1, A2, and so on and so forth up to AN, right? The probability of the sample space is sum of all partitions, right? So that make our calculation easier, okay? So let's see the example why this is true, okay? So the question is like this, okay? It's rather technical, but shouldn't be very difficult for you. Instead of rolling the die once, you're asking what rolling the die twice, fair die. And the question we're talking about is, suppose we are going to roll a die twice and we add the face values of the two rows. What is the probability that the sum of the two rows are less than 11? And immediately you can think about less than 11 have a lot of possibility, right? It's 1, 1, 2, 1, 1, 2, 3, 2, 3, 1, and 4, 1, 4, 2, many outcomes that is favorable to less than 11, right? But when you think about its complement more or equal to 11, okay, actually only have two possible cases, 11 and 12, right? Because adding value of two outcomes, you only have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Because the biggest is 12, 6 plus 6 is 12, right? So because you have 12, right? 11, up to 2, right? So if you want to say 2, 3, up to 10, you have to take less than 11. Looks like this, right? You need to take care of 2 up to 10, okay? Then our life is a little bit difficult. I mean, it's doable, but it's not fast enough if you do it this way. Rather, you would want to focus on the very last two. Look at 11 or 12. That makes our life easier, okay? Do know that the way I'm writing in this is already I'm doing a partition, right? I'm not talking about a particular outcome. I'm talking about all the outcome. 2 means all the outcome that lead to sum is 2. All the outcome that lead to outcome is 3, okay? Because 3 you can obtain by 2, 1 or 1, 2, right? 10 or you can obtain by 5, 5, right? Or 6, 4, right? Okay, there are many possible, but this 11 or 12 is easy to figure out, right? So if you partition the sample space into from 2 to 12, right? That's how I do it. How I do is I partition for AI, right? Some of this is I, right? So only you can see from A12, from A2 to A12, right? So obviously they are mutually exclusive, right? And collective exhaustive because that's what you all can get. And easily you can find A12. I mean, that is not difficult to see because 12 only come from 6 to 6, right? So that's why it's 1 over 36, okay? And you may ask why 36? Because you have 6 outcome for the first and 6 outcome for the second one, right? So just like you can list all the outcome in the table is 1 up to 6 and 1 up to 6, right? So how many boxes are possible, right? How many entry in the table is possible for 36? Okay, basically this guy, right? 6 over 6, okay? And what is, when you get 11, 11 is 5, 6 or 6, 5, right? So basically this outcome, this 2, right? So that's why 2 over 36, okay? And so what we now have is asking what is less than 11, right? So it's like this, okay? And this is equal to 1 minus 11 or 12. It's just the idea of complement rule, or what we call it, the more general version of the complement rule, right? So you just minus 2 over 36 and 1 over 36, all right? So that gives you 3 over 36. And that is the answer, 11 over 12. Is that clear? Is that clear how we do this rule? So that is the way that the calculation become simpler when you look from the other angle of the problem. Okay, so of course a little bit more technical, but I hope that is clear what we are doing. Although I don't expect you to answer such a complicated question, but it's possible, right? Because you should be able to understand what's going on there. Okay. Now, if it is no problem, then I just go to the next slide. Okay. We call the addition rule. Okay. This addition rule is a little bit interesting. The idea behind is related to axiom 3. Okay. Axiom 3 says the following, right? The union of two events, actually the sum of the two, okay? If the two events are mutually exclusive, okay? That means that if they're mutually exclusive, okay, this guy is 0, right? And we're asking the addition rule said the following: what happens if they are not mutually exclusive? Okay, if I just adding up the union of the events, okay, the union of them, okay, what do we have? Okay, it's still adding them, but we need to subtract the intercept. Okay, and in the other words, this addition rule tells you the following is how intercept and union are related. Okay, which is not there. We learn complement, but now we learn how intercept and union are related. Okay, and later we talk about how intercept are calculated. Okay, but that's we will call the multiplication rule, but we will keep it. But let's see the addition rule, what it means. Its union is equal to sum of them and minus the intercept. Okay, so that is looks a little bit complicated, but just before we go to the next slide, just going to say this rule is just coming from swapping the two things. Okay, you swap the two, you get the first line. Is that clear how you get the first one? Just like swapping. Okay, it's add and subtract. Okay, both sides. Is that clear what's going on? Okay, so if there's no problem, I just explain intuitive right, that's correct. Okay, we're not doing the proof. Okay, it can be proved, but we're not going to prove it. Just trying to convince you that this is right using the idea you learned from the kindergarten. Okay, so how do we prove that? Let's look at the graph here. So the idea of this, okay, is the following. Okay, so you will see this A, okay, the circle A, okay, is the probability of A, okay, and you will see the another circle, okay, that's B, okay. If you add them up and take away the intersection, okay, so if you add this and minus this, it's very clear that it should be equal to this A intercept B, A union B. Okay, the reason is being that a circle and another circle, you have overlapping in the intersection. You take away that, they give you the union. Okay, so that's the idea. Oh, that is almost very close to the actual proof you'll be doing in advanced math test, but that is exactly what it is behind. Okay, because you double count the intersection to take it away, and that's why how the axiom 3 would work, because the intersection is not there, so we can just simply add them. Okay, this intuition should extend to infinite case, but that is what axiom 3 said. Okay, is that clear what's going on here? Okay, it's like the kindergarten thing, right? Just like the overlapping the thing, then you just count the area, just like there's overlapping one, so take it away. Okay, so that is the addition rule. Is that a question? If not, then you're happy with that. Let's go to the example. Okay. The example is rather simple. With what it said is, I wrote a fair die runs. What is probability having even number or number bigger than 3? Okay. And even number will be a number that is 2, 4, and 6. Okay. And the number greater than 3 will be just 4, 5, and 6. Okay. So what is the question here? What we're asking is or. So the question is asking the union. Okay. Asking the union. Okay. Asking whether either of them is true. Okay. So you can easily see, you can directly calculate union, right? Which is you pick up everything there, right? The union will be 2, 4, 5, 6, which is what is here. Okay. The union is here. Okay. So since the fair dies, each outcome is equally likely. So union of this is just probability of 5 outcomes. So 4 outcomes, so which is 4 over 6, right? Because each outcome is equally likely. So end up with 2/3. Okay. So this is the way you would do if you can figure this 2 out. Okay, easily. Okay. You can directly go to here, right? When this is straightforward. Okay, the union is straightforward, you can go directly. Okay. So let's consider the case that when the union is not easily can be found, right? So how you can proceed is to look at the intercept, right? Because look at the intercept is much easier than look at union, right? Intercept just found the common element, they're done, right? So look at what the common elements here. 2, 4, 6, 4, 5, 6, right? The common element is 4 and 6. Okay, because you just pick up the same thing, only 4 appear twice and 6 also appear twice. Okay, 2 and 5 is not there because only appear in A or B, but not both. Okay. So then in that case, we can calculate the probability A is 1/2, B is also 1/2, right? And A intercept B only 2 outcomes, so it's 2 over 6. Okay. So then we use the addition rule. Okay. A union B is probability A plus probability B minus the intercept. Okay. So it's 1/2 plus 1/2 minus 2 6 is 4 6. Then it's 2/3. Okay. So you should get the same result here. Okay. Although it looks like a little bit detour for what we're doing, but I'm just showing you that this will be the important rule, okay, to connect ourselves between union or intercept. And that would be rather interesting or important thing later you will see. Okay. I hope that's clear. Okay. If that's okay, then I go to the next slide. So just go back to here, right? You can see I can directly calculate union. It's all the thing there. The intercept is over here, right? Actually, only 4 outcomes here. So 4 over 6, right? Because I didn't write here, but you can easily see what is outside. It's just 1 and 3, right? So we just the total sample space is only 6 outcomes, and that's why it's 4 over 6, right? I didn't write 1 or 3, but I think it's very clear 1, 3 is outside. Okay. Now I want to talk about this one. I think this one is a little bit more interesting. It's a condition table, where you would often have the data often end up in this form. Okay. So condition table is what we said here is what it means is also we mentioned in our first topic. Here the first entry is 15, means this there is 15 males also pass the exam. Okay. In that case, this is more like the idea of intercept. Okay. In the condition table, everything is intercept, right? So here we have 25 male which failed the exam, so everything is intercept in this table, right? So the question probably you want to know the union. Okay, sometimes you want to know the union, and of course union you can also read from the graph. Okay, but now let's show you how can we do this using the probability rule here. Okay, the question is suppose I randomly draw a student from this sample and asking how many of them is a male or pass exam. Okay, so let's do the case where you can easily go through the table. Okay, either a male or pass exam. Okay, how many students actually is a male and pass exam? Okay, and you can easily figure that out. Is it will be 15, 25, and 20. Okay, why? Because 15 and 25 are male, and 20 are actually pass exam. Okay, so that's why we have at the last bullet point here we have this. Okay, actually there's 60 of them has actually either a male or pass exam. Okay, and how many students are there total? We have 80 students. Okay, so that's why you have 60 over 80 is 0.75 probability that you draw either male or pass exam. Okay, you can easily see that. Okay, this one I can find the union is rather easy. Okay, but you can imagine that if this table is huge or big, then your life will be very difficult. Okay, so sometimes because you already calculated the intercept, right, or somewhat easier to calculate this way. Okay, so let's see how we can use the addition rule to simplify our process. Okay, you can imagine this is easier when we have a large table. So how can we make our life easier? Why easier? Now, how do we make use of this table? Look at the probability of male, okay, which is coming from, maybe use another color. I don't know. Orange is good. Okay, 40, right? Because total number is given by the n column or n row, right? It's 40. For the victims, half of them is male. And look at how many have passed. It's here, 35. Okay, and probably pass is just 35 over 80. Okay, and how many of them are actually male and pass? From this number, 15 over 80. Okay, 1.875. So we just add up the first two minus the last one, we get the answer. That is the exactly what we have the addition rule. Okay, you can easily see that if you have very large table, right, then you can find the total very easily. Right, you just need to find a total and pick a particular point is fine. Right, rather than if you have a long table, you add up everything there, then your life will be difficult. Okay, so that's why, especially when you have very complicated intercept, that's why this rule will be very helpful. Okay, of course, everything just illustrate the point why this rule is true and why this is convenient. Is that okay? If there's no question, I guess I can go to the next one. Okay. So here is another rule that will be used, is called the total probability rule, which says it's more like a divide and conquer idea. Okay, we partition the sample space, okay, into B and B complement. Okay, so and then what we said is A is equal to A intercept B and A intercept B complement. Okay, so this looks a little bit not easy to see, but you look at the graph, you will see easier. Okay, so look at this example. Okay, again, we have that rolling a die already. Okay, so A is the big circle here. Okay, the big circle you can divide it into two parts. One part is the part with intersect with B, which is this part. Okay, this is the part A together with B. Okay, and the other case is the part that A without B. Okay, so basically, probability A is sum of two parts, A with B and A without B. Okay, so that is what it means. Okay, let me repeat the statement. This statement is probability A is A with B and A without B. Okay, so it's very true. It's very simple, right? But this directly follows from axiom axiom free, right? You can prove it. It's very simple idea. Okay, but we are not going to do the proof, as I said, because saving time. So here we have the idea is because this is divided into B and not B, but it's just saying the following. If A1 up to AN is partition of sample space, B will be sum of all this. Okay, graphically you can see, let me draw a diagram to make sure that it is easier to see. It's just like the following. So I have a sample space here. This is my sample space, okay? And this is my event A, okay? And I can cut, this is called A1. Oh, I should call this B, right? To be consistent with the, here. This is B, A1, and this is A2, and this is A3, and so on and so forth, okay? And the poly B can be decomposed into the part B with A1, B with A2, B with A3, B with A4, B with A5. Okay, because look at the graph here, right? Just like this is the part with A1, right? And this is the part with A2, and this part with A3, and so on and so forth, right? A can be decomposed. B can be decomposed. B with A1, B with A2, B with A3, B with A4. Okay, as long as these are A1 up to AN is partition. Okay. Before we just talk about B and B complement, but we just little bit more than that. Okay. Is that clear? What's going on? Now we want to talk about the odds before the break. Okay, odds is somewhat very interesting thing related to what we observe in the world. I think I probably call application. Okay, odds. Okay, is of course it's a very complicated idea. The reason is because there are many definitions. I think that's called British odds and American odds and odd in favor, odd against. So I think we just follow the definition of the book. Okay, that's how we define odds. Okay, it's very simple, just like event problem odd ratio in favor of A will be just A over its A complement. Okay, and against will be A complement of A. Okay, and very often we don't usually mention in favor of. Okay, we just say in favor, we just say odd ratio for A. Okay, will be just meaning this one. Okay, so the first one will be the thing usually we are talking about. When we don't add any qualifier, we always mean the first one. Okay, odd ratio for A is just A over its complement. Okay, obviously that fit our intuition that the higher the odds, right, the more likely it is, right? And people in the real world sometimes use probability and odds interchangeably because that is proportional to that, right? The higher the odds, the higher the probability, of course. But the idea of odd is just not different from probability, is because it's not limited to 0 to 1, right? Probability is always 0 to 1, but odd is not, right? It can be very large, can be very small. The only limitation is not negative, right? Is anything non-negative is acceptable, but let's see what is important. Okay. Later, immediately we'll say odd is actually related. Is that okay for odd definition first? Okay, there's nothing to remember, but just that's the definition. Okay, but what is it? Is the odd is actually a term that used in gamble industry. Okay, or what we call a fair bet. Okay. So usually when we talk about odds in the real world, sometimes they call 4 to 1 bet. Okay, which means that if you win, you got $4. If you lose $1. Okay, so that is what it means. Okay, and what is a fair bet? Okay, which you can define in the next class, or next week. You will say the expected value of the gamble is 0. Okay, but we'll talk about that. You know that later. But how do we define fair bet in this idea is if the odds, okay, using the betting, okay, is exactly the inverse of this one. Okay. So I give the example immediately now. You will see why the bet you see in the casino, okay, it will be fair if that is the inverse of the odd ratio we mentioned, okay, or if you want just exactly this one, okay, because these two are inverse to each other, okay. Now let's see this one, okay. Let's see this example. Is you roll a fair die once, okay. What is the odd ratio in favor of 6? Okay, and let's define odd ratio, right? Odd ratio will be the probability that let you 6 and 1 minus 6, right? So this what we have is just like 1/6, right? And this is 1 minus 1/6, right? So this is 1/5. Okay, and what should be the fair bet? Okay, it should be the case when, because you lose, the 5 outcome you lose. Okay, only 1 outcome you win. Okay, when you win, you must win 5 times more than you lose, right? Because 5 times more likely to lose than win. Okay, so that's why if it's fair, you have to win $5, right? When you lose $1, right? In that case, it's fair. Is that clear? Because you're 5 times more likely to lose than win. So when you win, you need to win 5 times more than you lose. Is that clear what's going on? Okay. So that's why when you look at the simpler cases, I toss a coin, okay? What should be a fair bet? Okay, you can only bet either head or tail, whatever. It must be the case, okay? The odd ratio is a fair coin, is 1-to-1, right? Because in a fair coin, probability of say head, 1 minus probability head, okay, which is 1/2 over 1 minus 1/2, which is 1-to-1. All right. So it means that if you are betting on a fair coin, it must be the case that if you win, okay, you get $1, you lose $1. Okay, if you try to bet whether the head comes out, okay, if you win, you get $1, you lose $1. This is exactly what you were expecting when you go to Monte Carlo casino. We're betting whether it's a big or small, right? Is you get if you win, you get double the amount, right? So exactly what this bet is. Right, so that's exactly what's going on there. And I guess that's the meaning odd ratio. So I want to end this because break up with a concluding remark, right? Here we can see we're trying to calculate whether given what we know from the probability, what is the odd ratio and what is the fair bet. Okay, and we can do it in a reverse way in application. Okay, because sometimes we don't really know what is the probability of certain event, right? But we can observe what the odds. Okay, for example, we observe the stock market, right? The stock market, more probably if the fair efficient, it tells us how likely certain things happen, right? If say interest rate goes up, the stock price goes down, so on and so forth, right? By looking at the stock market or the market, whatever, the betting market, or look at horse racing, so the easiest look at horse racing, we probably don't know which horse is going to win. But by looking at the odds, okay, we can go back to ask ourselves, what's probably that horse would win? Right? Suppose the odd is like 1-to-1, right? Then it's likely the half of time he's going to win the horse. So on and so forth. So basically the odd ratio, look at the odd, can go back to we can know what does the market think about the probably something happen. Right? That's why look at say the stock market, you probably try to guess what's going on in the stock market, right? But probably if you look at the futures, look at the option, look at the warrant, look at those things can give you some idea what's going on, right? I think I should end here with a break of 10 minutes. So we will come back at 1:30. So go around to ask you have any question.
应該如果唔超過，應該咁樣我讀翻試書嘅，睇你先去做嗰對你嘛，應該冇超過嘅3我可以將佢非常
So, so now we continue. So I hope there's no problem for the odd ratio. Just this is definition, okay? So we continue to talk about the contents of probability. So this is a little bit more complicated. I guess if you do not do the advanced math, then probably you haven't heard about it. Or, but anyway, so let's start from scratch, okay? So, but this one is exactly what is important for why we learn probability, is how we update, we learn things, okay? So here's conditional means suppose we know some of them is true, okay? Is there anything we can learn? We need to update the probability, okay? So here is the comes with definition, okay? We're not going to prove this is true, okay? There's a proof exists to prove it, but we try to argue that this is the right thing to do, okay? So here, this notation means the probability of event A happen, given that B has been shown to be true, okay? So we know B has true. So what it means that B complement is false, okay? So B is true, B complement is wrong, okay? So what is said is, remember A, you can, total probability rule said the following, right? Probability of A can be decomposed into two parts. What is it is part with B and the part with B complement, okay? So what now it said is we know B is not true, okay? So that means that this guy is not there, okay? This guy is irrelevant, okay? So that's why you will see the numerator, okay, is exactly this guy. Why? Because B complement is wrong. It's no longer true, okay? And the next question you may ask now is why we have a denominator for the B. The reason is being that this comes from the axiom 2, because the sample space is 1. Okay, so you have to divide the sample space probability that makes everything 1. Okay, why this is the case? Consider A and B the same thing. Okay, if A and B are the same thing, you should expect it's 1, right? Probability B given B should be 1, right? And you should expect the numerator A intercept B is 1, right? It's probably B, right? right? If A is same as B, okay, this is B given B, okay, and this B intercept B, which is same as B, right? And the numerator is probably B, the denominator is probably B. This is 1, right? The same thing, right? So that's why it's basically coming from the idea that the sample space must be 1 because the sample space shrinks, right? Before you said it's sample space is S, but we now know it's not no longer S, it's B, so it shrinks, okay? So that's why you have to divide it. When it shrinks, that means that you have to enlarge other parts, okay? So that's why I divide the probability B, okay? There's a proof, there can be a proof behind, but for the sake of our class, we don't prove it. You take this as a given, as a definition, so we don't prove it, okay? But we almost give you a proof, okay? Almost a proof is there already. It's almost a proof we gave you already. It's normalizing to 1, okay? So is there any question? If no, then we see the diagram, then try to hopefully can convince you this is right. So we are trying to give you example, trying to convince you that this is correct. Okay. So the idea is following. So I have rolled a die once, okay? The sample space 1 to 6, okay? Again, we have even number 2, 4, 6 as E, large number 4, 5, 6 as large, and the E intercept L will be just this guy, okay? So the question we have is, okay, suppose we know that someone told us that roll a die is large, okay? We don't know more, but we know it's large, okay? With this information, okay, the question is, how likely that actually we have even number, okay? So in other words, suppose you are told that it must be 4, 5, or 6. 1, 2, 3 is not possible, okay? Given you know it's 4, 5, 6, how likely we having an even number, okay? Is that clear what we're asking, okay? Is you are told that 1, 2, 3 is not there, okay? 1, 2, 3 is not there. There's a rumor, there's a report telling you it's not 1, 2, 3, okay? So now, actually you can see if you try to change this question directly, right? Now the new sample space is actually L, okay? And the event E, even number, is just only 4, 6. Why? Because you know 1, 2, 3 is not there. It's only with 4 and 6, okay? So the probability E given L is just 2 over 3. Why? Because L, the sample space only have L, it's just only 3 outcome, 4, 5, and 6, okay? The event only 4 and 6, so it's 2 over 3. Is that clear? Why it's 2 for? Because the new sample space is only 4, 5, and 6, right? And the even number is only 4 and 6, so that's why 2 or 3. Okay, is that clear what's going on here? Okay, so you may say if I do this every time, I have to go back and ask shrink the sample space and do things a little bit more difficult. Okay, so that's why that's come the convenience of the definition actually can be proven. Is you can follow the idea of this. Okay, the probability E given L is a fraction where the numerator is the intercept. Okay, the denominator is something is know is true. Okay, and then the numerator is E and L. Okay, what is E intercept L? Only 2 outcome, right? E intercept L. Okay, probably you should know by now, right? Should be only 4 and 6. Okay, so that's why it's 2 over 6. Okay, and L only three of them, right? So 3 over 6. Okay, so we end up again 2/3. Okay, so regardless of what you're doing, that is you get 2/3, right? But you can see that this one is easier, right? This is a shortcut because you don't need to string the sample space and do everything, right? That makes our life easier. Okay, and the actual proof behind this formula is very similar to what I'm doing here. Just change them to be very general things can be done, but we're not doing proof. So that's why we just take it as a definition of conditional probability. We're not proving anything why this formula is correct. Okay, this can be derived from the 3 axioms. Okay. Is that okay? Any question? Okay. Later you will see why this definition is important very soon. But let's keep in mind this is a definition. Okay, we will talk about several rules related to this one. Okay, so let's see again the example we have here. Okay. Oh, sorry. Probability. Remember the question is probability E given L. Okay. So before the sample space is everything there, but now that's large. Okay. So this is the new sample space is here. Okay. This is a new sample space. Okay. The new sample space only have 3 outcomes. Okay. 4, 6, and 5. Okay. And what is even number? Only 4 and 6. So that's why it's 2/3. Okay. So that is how we justify this idea. Okay. Just like the sample space strengths. Okay. And that's why everything probability have to be scaled can get bigger, right? Because before everything add up is 1, right? So now we have to get every outcome add to 1. So we have to divide it by a number less than 1, okay, to make everything scale up. Okay, this original probability here, okay, everything have to be get bigger so that sum of them is 1. Okay, so that's why we have that. I hope I can convince you this correct, but if you are not convinced, just definition. Okay, not going to worry about that, because once you learn further, then you will know why this is. Okay, but just here I have a very simple example. Okay, just to show you how you can do it, right? Suppose I have A is 0.2, B is 0.5, the intercept is 0.3. What is A given B? Just directly apply the formula, right? So you get the answer. Okay, this is very trivial. Okay, but I put it there because something similar to assignment, so you know how to do. Okay, is there a question? Nothing deep here, just put in the formula. Okay, I'm not going to spend time on it. Okay, now here comes the next rule. Okay, which you may see clearly. This is nothing but how we write things. Okay, so just to remind yourself, if you happen to have your notes with you, you just remember we learned just the formula A given B. Okay, is just the following is a fraction for B, right? Probability A intercept B. Okay, so this is what we learned, the definition of conditional probability. Okay, you just multiply both sides by probability B. Okay, that's how you get this guy. Okay, what you're going to do is multiply both sides by probability B. Right, so this cancel out. So you get the first one, right? The second one is just say what is, you swap A and B. Okay, A is B, B is A, then you get this one. Right? You call B is A is B, you get this one. Okay. Or if you don't like, you can write what is probability that B given A. Okay. You can do the same thing. You also get another one. Okay, that's how you get the two equations. Okay. So what here is well, we define how to get the intercept. Okay, the intercept will be just A given B times B. Okay, or a B given A times probably A. Okay, so immediately you will see why this is useful. Okay, and because sometimes you do things sequentially, that makes thing easier when you put in this way. Okay, you will immediately see the example that justify why this is a good one. Okay, but before we do, I don't see shouldn't be any difficulties to understand this formula because it's multiplication, right? Just coming from definition. Okay. Yes. So this is the example that usually you will see in textbook, right? And there's an urn with 3 black balls and 3 white balls. Okay. And the question is the following, right? So you have a urn, we have 3 black balls, okay, and 3 white balls. Okay, so that is the question that is given here, 6 balls. Suppose you're trying to draw 2 balls from the urn, okay, and you take it without replacement. So you take it and take it again, okay. So you're not putting back the balls. What's probability both balls are black? So you want 2 black balls, okay. So in order to do this question, from the first principle, you have to think about what are all the possibility, right? And here's a shortcut, okay? The shortcut how to do it. Okay, let's see how we can do it by shortcut. Okay, first we define, let's make it easier, we define B1 to be the event that the first ball is black. B2 be the event that second ball is black. Okay, so what is probability of B1? Okay, the first time what you draw is you have 6 balls. Okay, what is likelihood you get a black ball? Right, 3 out of 6, right? Because you close your eye and draw it, which is half, which fit our intention, right? Because equally white and black, so it's 1/2. I don't think that is controversial. The second one is a little bit more uneasy, but once you draw a black ball, what do you have here? Once you draw a black ball, you only have 2 black left, okay? And you still have 3 whites. Okay, that is what you get in the urn. Because once you draw a black ball, given the black is true, B1 is true, what is B2? Okay, what you left is 5 balls, only 2 balls favorable to that, so it's 2 over 5. Is that clear what's going on here? Okay, so that's why when we ask the question, how likely you draw 2 black balls, it just, you use the multiplication rule, okay? You have black, probably back B1 and B2 given B1, okay? And that you just put in the number there, okay? 2/5 over times 1/2 is just 1/5, okay? So that is the idea how you can derive that. Okay, and I hope that's clear what's going on here. Okay, is that clear what's going on here? Okay, can I go to the next slide? The no question. Okay, question. And you may wonder we have this multiplication rule, but actually you have been using it. If you're in the high school, you learn the tree diagram. Okay, look at the tree diagram. That is actually what you have been doing. The multiplication rule you have been doing. Okay, so let's see this example and justify how you learn it from your high school. So that first drawn, okay, we have 3 black and 3 white. Okay, B1 is first time is black 1. W1 is when the first drawn is a white ball. Okay, because it's equally likely that this can happen, right? This actually 3 over 6, right? But I just simplify to 1/2, right? And once you draw the first black ball, what you left in the urn is just 3 white and 2 black, right? And if you draw the white ball, then you have 2 whites and 3 blacks, right? And in that case, if you find once you have 3 white and 2 black, you may also draw a black again, but you only have 2/5 of likelihood, right? Because that is over 5 balls, right? You have 2 black. If you draw a right ball, then it's 3 over 5. Okay. Same idea here. If you have 2 white and 3 black, then the black will be 3 over 5. The white will be 2 over 5. Just opposite case because it just depends on what is drawn the first one. Okay. And I think you do recall that in the high school, right? What is the probability that you end up in here? Okay. How you get it? You multiply backwardly, right? Look at this branch. look at the number here, multiply this number, you get, how you get this branch is 1/5. What is behind in this is this multiplication rule. Okay, how you get it this branch, what probably that is just multiply this and times this, right? That's how you learn in high school. Okay, what is behind from this multiplication along the branches is the multiplication rule. Okay, because this is conditional on this is what happened, right? So just multiply this back, is what's going on. Okay, you can easily see that this rule generalized to more layers of branches, right? You just keep multiplying up to the root. Okay, so although I didn't say it out, but it's clear that this multiplication rule apply when you talk about a multi-layer tree. Just keep multiplying. Okay, is there any question? Okay, is that okay? That's okay. Then let's talk about the other rule, which is sometimes people in the online or textbook, they would call this guy, sometimes they call this total probability rule in some textbook. Okay, but that's no different. The reason is being that when we learn the first line, it's called total probability rule, right? That's what we learn from our slides. And because of the multiplication rule, right? A intercept, let me use a color. A intercept B, okay? It's just A given B times B, right? A intercept B complement will be A given B complement times B complement, okay? So that is exactly the same idea, okay? And I don't see the difference. You call the first line total probability rule or below, okay? And you probably ask why we have this thing, okay? At the end of today, probably we go to the base rule, you will see why we talk about this, okay? Because that is the way we do calculation, okay? So this is very important formula, because this formula help us to do the calculation later, very soon, okay? So, but that shouldn't be nothing difficult, because just combining the two rules we have, okay? So just remember A is part of A with B and A without B, but A with B is just A given B times B, and A without B is A given not B and what happened not B, okay? Is that clear what's going on here? Okay? I'm sorry that today we have to do some mathy thing, but probability you cannot go mathy. I mean, is that okay? Okay, so I think this one is a good example again to see why we need this. Okay, so let's see the example here. Okay, so we are given two bets here. One is called A, one is called B. Okay, and the first bet we have 4 white balls and 1 black. The other one has 1 white and 1 black. Okay, and you close your eye and choose a bet, and then close your eye again to draw a ball there. Okay, so that's why you don't know which ball, you don't know which bet you're drawing from. Please close your eye and just pick up a ball over there. Okay, but the question is, what's probably there is white. Okay, so here we would be doing is what we first apply the total probability rule here. Okay. White ball can be a white ball from bet A and white ball from bet B. Okay, so that's why white intercept A and white intercept B. Okay, so that is what we know. And then we apply the multiplication rule again. Okay, white and A is white given A times probably A. Okay, and the same here is white and B will be white given B times B. Okay, and of course, if you know the rule, you can just apply second line directly. But if you don't, you forget, then you just can go from the first principle. That's fine. Why we do this? Because we do know that how when you get A and B, right? Why A is 1/2 and B is 1/2. Okay. The reason is being that you close your eye and pick a bet in a random. So half likely get A, half likely get B. Okay. And once you go to A, we know there are 5 balls there. 4 of them are white. So that's why you have 4/5 here. Okay. And similarly, if you go to bet B, you have 1 white. Okay. So that's why only 2 balls. So 1/2. Okay. So we'll compute, then you will get 0.65. Okay. So that is how you get the answer. Okay. So looks complicated. You divide them in 2 parts and calculate. So that's why this is more like, as I said at the beginning, this is called divide and conquer strategy, right? Calculating W is a very complicated object, right? But you divide them, you partition the sample space in 2 parts, you get A or you get B. Okay. And when you get A, it's very easy to calculate. B is also very easy to calculate. So that's how you would do probability problem like this. Okay. Particularly in very complicated scenario, you would cut it into multiple parts, right? That's how you divide. It's like division of the problem, right? Is that okay? Just like you can think about the case, you have a very complicated machine like a car, right? What's probability that the car doesn't work, right? Can be attributed to the front end doesn't work, right? The wheel is error or the back is error, right? So you just cut into multiple pieces and each part you can handle it easily. Is that clear what's going on? Okay. So I hope that is more or less okay. Okay. Any question? If no, then we go to the next. Okay. So this is just to trying to show you again the tree diagram if you learn it in high school, right? So first asking you whether A or B, and there's 1/2 because you close your eye and randomly chose A. Okay. And the next stage is if you get A, right? You will get 4/5 is white and 1/5 that is green. Okay. Oh, sorry, I changed it to because white and black is not easy. I just assume to white and green because I don't want A and B to confuse. Okay. So A intercept W, right? It just you multiply backward, right? Just that is called the multiplication rule, right? So that's how you get A and G. And similarly get all the numbers. Okay. So the question is asking the following, right? What is the probably you get a white? Okay. So basically just this guy and this guy, right? Because the other 2 branches are related to green, right? Or black, but anyway, so that means that you only need this number and this number. You just add them, right? Because each branch of tree is mutually exclusive, right? So that's why I just simply add them by axiom 3, right? So that basically this item and this item add together. Is that clear? Okay. That's how you learn. If you want to do a tree diagram, if you're more a graphical person, this is maybe helpful. Of course, if you able to read the math symbol, then it's easy to do what we done in the last slide. If you are more graphical, then this is easier to handle the question. Is that clear what's going on? Any question? Okay. If no, then we go to the next one. Okay. Once with this, then we can do our most important bank-based theorem. Okay. So now we go to the very last one. Okay. Almost the last one. We define the term of independence. Okay. And independence means the following. Okay. Means that idea is like the 2 events are independent. Okay. If I tell you whether A happen or A complement has no difference. Okay. Saying suppose the following, right? The question is now here, what is maybe use the red color, right? This is probably A given B. Okay. If whether I tell you B actually has no different, same as before, they're independent. Okay. Say for example, I roll a die. Okay. Then I don't know whether it's 1 to 6. Okay. But you tell me today is sunny day. Okay. They're independent. Right. So that is independent. Okay. And right, very often we talk about independent in the news, right? Our expert in the government, when someone got the vaccine and died, and they said independent. Okay. And how they can prove it? Okay. They would try to look at, okay, the death rate of a guy who died, how likely it is, and look at those people who took the vaccine, how likely they die. And if they look at the probability is very similar, okay, then they say the vaccine has no independent. Right? That's what actually they do, right? Actually they do, right? I mean, in statistics, you can prove taking the vaccine actually say 10 people die, but if every day 10 people die, then there's no difference. Okay, so that is how they do it, right? And B given A, same as B, there's no difference. And you may think that the first bullet point and second bullet point are different thing, okay? But they're the same, indeed they're the same, okay? The reason is being that that is our definition, right? The probability of A given B, okay, is just A intercept B times probability B, right? And if, okay, it is same as A, okay, if the first line, if the first one is true, okay, it will imply this is true. Can you see that? Because if the first line is true, this is just probability A, right? And you multiply the denominator to the other side, you get the third line, right? And easily you can see this argument will extend to the second one, right? So that's why I said 3 of them are the same thing. Okay. So if they're independent, the multiplication, the intercept is just multiply. Okay. So that is the very important definition, or you may say, or you can think, is how the intercept can be found. If they're independent, you just multiply. Okay. This one looks very trivial, but this one is, I guess, it's the most important thing you will be using for the rest of the course. Okay. Because independence imply you can just multiply 1 by 1. Okay. And that's behind the sampling idea. If you do the sample independently, right? So the probability of you get the particular thing, you look at each observation independently. Okay. You don't need to worry about how you combine things. Okay. So they happen together, you just multiply. Okay. So that is very important, although you may not aware, but almost the rest of our course will really depend on this. Okay. That's why you have the randomness. We draw a random sample. Actually, probably you will know later. This is rely on this. We make every calculation possible. Okay. If that is not possible, our life will be very difficult. Okay. So this definition, I guess I don't need to go further on this, but this example, if A is this, and B is this, and A intercept is this one, okay? Asking if they're independent, okay? So how you can prove it? You can just multiply them, but it's not equal to the intercept, then you are done, okay? So it's very simple just because definition of this guy, okay? Of course, you can also do this calculation, what is probability A given B, okay, by this, and this is not equal to probability A, then also you can also do that, right? Or you can prove in this way, right? B given A is not going to probability B. You can prove it. I mean, I'm not going to do it here, but you can actually check it by yourself if you want to. You give this, you can show either way will be fine. Okay, you can use the way I use in slides, or you can do the other two way, one of the two one of the three will work. Okay, because we prove it, right? Got the same thing. Okay, independence, I think it's very clear what's going on. One remark I want to mention is very clearly independence and mutually exclusive cannot happen at the same time. Okay, because mutually exclusive, when we said mutually exclusive means the intercept is empty, which is 0. Okay, and the addition rule means that adding up, it's just adding up the same. Okay, and independence means that intercept is just multiply 2 together, right? And the addition rule means that you can simplify in this way, right? Add them up and minus their multiple, because it can be simplified because of the definition of independence. Okay, and these four bullet points are mathematical expression, but let's understand why they're different, right? Because mutually exclusive means that if you know A happened, B cannot happen. If you know B happened, A cannot happen, right? So knowing whether one happened, you know the other thing. But independence said whether A happened or not doesn't help you to know B, right? Knowing the sky is bright doesn't tell you what is the role of today, right? I told the con is the result is independent of the temperature or the weather today, right? Maybe we like to hear, but say temperature in United States, right, is independent. Okay, so that is the idea. Is that clear? Okay, so that's why when you say an event, they're independent, they can't be mutually exclusive. And when they're mutually exclusive, then they can't be independent. Okay, so that's why you can play the word, say independence and mutually exclusive are mutually exclusive, right? Because if this is true, this is not true. If this is true, this is not true. Okay, but they can be both wrong, right? They cannot be both true. Okay. Now finally, we talk a little bit about the base rule. Okay. So I just highlight why we need them. I don't know if we have enough time to cover, but why we need Bayes' theorem. The idea is what we call the statistical learning. Okay. You try to learn from new information. And that's how science progress. That's how when you do artificial intelligence, machine learning how to learn. One of the main way they learn is called the Bayesian learning. That's what from this formula. Of course, that what we mean. There's a non-Bayesian learning, but this is how we call how rational people should learn. Okay, and this learning the formula looks very complicated. Okay. But this is nothing more than the definition, okay? Remember, probably A given B, the definition is just the following. The denominator is probability B, okay? The numerator is just A intercept B, okay? And how you get from A intercept B to this guy? Just the multiplication rule. Okay, so here the Bayes' theorem is, in terms of math, is nothing but just definition of conditional probability plus the multiplication rule. Okay, so by itself is nothing. Math is nothing deep here. Okay, but there is a very important consequence here. Is you can see the main thing. The main thing you can see is with B given A and you have A given B. Okay. So that is the key of this. Okay, that's the main key of this. Okay, now you obviously confused by what we're doing, as I do when I was a student, if you haven't seen that before. So let's see the example, then you will obviously see why we're doing. Okay, so it's very confusing right now, but very soon you'll see why this is important. And this is invented by Bayes, I think in the 1920s. Okay, I think it's like hundreds ago. It's not very long. Okay, but let's see why this is important. Okay, we proved it already. So let's skip this graph for the moment. Later you understand what is going on here. Okay, so let's see this example as we all do. We often see it when we do a medical test. Okay, so the question is following. Okay, I don't know if we have time to go over everything, but let's see the question first, and you will appreciate why we are doing this. Okay. So now it's a COVID time, so probably we are over that. Maybe next year I don't use this example, but this year it's still relevant. So consider a case where 40% of the population is infected. Okay. So first is how you come up with this. Okay. This is our working knowledge. Okay. And this is the knowledge that we are going to update. Okay. This is something we're going to update later. You will see immediately. Okay. So now we have something we rely on some technology that's imperfect medical test. Is a test that we are going to use. This test is imperfect. Okay. If this medical test is perfect, then we don't have probability. Okay. So we have something like if a guy is infected, he will get positive result with 80%. Okay. So this test is 80% accurate. Okay. So which means that you will have the 20% that is a false negative. Right? 20% they get negative result, but it's a false, right? So 20% false negative, if you want to say it, right? False negative. And you pick up a random guy uninfected, okay? And it will still have positive result of 0.4, okay? So that actually means that this is 40%. You have a false positive, right? False positive, okay? Because 0.6 you get right? If no disease, 0.6 you get it right? But 0.4 you get wrong, okay? So this is not rather inaccurate test, okay? The question is asking that is something we want to know is we have some information from that guy. We ask a random guy, okay, to do a test, okay? The test gives us a positive result. What we want to know is how likely that that guy has the disease, okay? So let me repeat the question again because it's very important. I'm not sure we have enough time to go over the problem, but it's important to know what we are doing, okay? The question is, if I have a random guy on the street, okay, what is the probability to get infected, okay? That is 40%, okay? Because I pick a random guy, I do nothing, I'm not going to do anything, or the guess that guy has a disease, 40%, okay? The question now is, I'm going to give him a test, okay? If the test negative, probably, I mean, you're not going to, you're going to say he's less likely, less than 40%, right? If he got a positive result, okay, you will say he's more than 40%. You cannot say for sure 100% unless your test is 100% correct, right? So what is the number, right? You know it's more than 40%, okay? The question is how much more, okay? So let me repeat it again because it's very important is we're asking the question, asking the probability is in fact a given positive result. So which means that I do a test on that guy, okay? That guy got positive result, okay? What do you think this guy has the disease or not? Okay? Is that clear? Okay? So how do we do that? Okay? The question is like this, okay? A is the event getting infected. B, you get positive result, okay? So probability A is 0.4. Probability B given A is 0.8. Probability B given A complement is 0.4, okay? Asking A given B. So infected given positive result, okay? So you can see our technology is 0.8, right? So we just try to swap it and try to see what's the answer. Okay, is that clear what we're doing? Okay. But you do look that we have the originally what we have is this guy, PA, okay? Probability of A is 0.4. So now we get positive result. We want to know this update, okay? A is what we know at the beginning. Now we know B had happened, okay? So what is P given A? But A given B, sorry. Is that clear what we're doing? Okay? So I try to be quick, but we'll go back again next time is we'll try to prove this idea A given B, okay? is going to be two part probability A intercept B, okay, and probability B, okay. And I guess I should stop because I think some of you will be hurried for the next class. So let's stop here. We'll do it in the next class, but I guess it's clear what we're doing here. So we'll see you on Wednesday.